we have a trapezoid rule problem, pretty straightforward. What's one thing we have to be careful about? Good, the intervals are uneven, so I can't just do a big factoring problem. I'm going to have to do each individual trapezoid. Luckily, there are only, what, 3 of them? So 1/2, the width of the first one is 3. Does everyone know where I got the 3? Yep, 2 to 5, and then 10 plus 30 plus 1/2 times 2, 30 plus 40 plus 1/2 times 1 times 40 plus 20. I'm running out of room, so I'm just gonna put the 60. Y'all okay with that? This probably would be non-calculator, so you may want to practice doing a little bit without a calculator. Open response, you could leave the answer this way. Multiple choice, you'll have to pick out the answer. 40 divided by 2 is 20. 20 times 3 is 60. The 2 and the 1/2 cancel, so 30 plus 40 is 70. So 160. It's not that bad if you write it down. If you just look at it and try to do it in your head, it seems a little overwhelming, but if you start writing those down, it's not too bad.
Please pardon the interruption. I need to see the following students in the high school office: Greg Spencer, Paige Morgan, Colby Porter, Jessica Reed, Levi Hicks, Dustin McGowan, Madison Frank, Hannah Brownfield, Jacob Yoder, Bryson Zerba, Tamison Griffin, Hannah Myers, and Thomas Hicks in the high school office. Thanks.
Okay. So what we're going to look at today is called the fundamental theorem of calculus. And this is a little graphic to kind of help you discover the fundamental theorem of calculus. This is a graph of some function f of t, and then we have a point x. That x is movable. It's a variable x. So we have this function here. We could find the integral at any point x. And so on this function, I have the integral calculating. Now, your calculator would do that. It would take a while, but it would do it. Now, what I'm going to do next is I'm going to plot the graph of the integral. So if I have x is 1.6, I'm going to plot the y value as 0.16, which is the area that's been accumulated. And so that is a different graph. I'm going to call it G. So you can kind of see what I mean by that. You see how the green is calculating the integral, and this is just plotting that. Everyone see that? For whatever weird reason I want to do that, that's what I've got going. So I have the integral of f of t, and I have defined that integral to be g of t, or g of x, whatever you want to call it. I could find the slope of the tangent line of g if I wished. And I want you to notice something about that slope of the tangent line. Is it the same as the original y value? So the derivative of the integral is just the original y value. So that means the derivative and integral undo each other somehow. They are inverses. Crazy, isn't it? Slightly crazy. The derivative and the area under a curve are inverse operations, like an x squared and a square root. They undo each other. Interesting. So, write this down. The fundamental theorem of calculus, part 1. Part 1 is a made-up. Every book is going to call part 1 different than than every other book. There are essentially two parts to it. It's really one theorem. Some people teach this part first, and thus they call it part one. Some people teach the other part first, and they call it part one. It doesn't really matter. They're just two parts of the same theorem. We'll learn part two tomorrow. However, the important thing is if you have f of t that's a continuous function, and you define g of x to be the integral from some value a to x of f of t dt, then g prime of x is f of x. In other words, the derivative and the integral are inverses. That's the main thing I want to get out of this today. We will revisit this theorem in its technicality later. But today, the big thing is that the derivative and the integral undo each other. Very difficult to visualize that. It is not at all intuitive that area and slope would have any kind of relationship. And that's why this theorem took so long to develop. I don't know if y'all know when Isaac Newton lived, but it wasn't very long ago. Calculus is, relatively speaking, a very, very new form of mathematics. And it's because it took people a really long time to figure this conclusion out, because it's not intuitive. It took some physicists to think about velocity, probably. That would be my guess. I put a picture up there, but to me a stationary picture just doesn't do it justice. The visual I gave you on the graph earlier did a little better job of showing you that relationship. Okay, so an example. One example. If I have the integral from 2 to x of t cubed dt, then what is g prime of x? Turns out it doesn't matter what the bottom number is. It's just x cubed. Because the derivative and the integral undo each other. So if I look back up at the theorem. Good question. It is kind of a notational thing. But if I look back at this function here, and the way I've defined it, I have t as the function. X is a separate variable from t to define that second function, which is the integral from a to x, which is more of it's still a variable, but it's a different variable than t. If you accidentally put x on both of those on the AP exam, they'd probably give it to you. But it's because of the way, when I made this, I had to use two different variables to make a calculator program work to define that. Does that make sense? Good question, though. So, the integral from a to x of f of t dt, if that's g, then g prime is just f of x, which does appear to be a variable swap. We will get into a little bit more technicality on that another day. Again, today, our goal is to notice that they are inverses. G prime would just be x cubed, just be the function, the integrand, because the derivative and the integral undo each other. Whoops. Okay, so we want to look at some basic integration rules. If derivatives and inverses are truly, or derivatives and integrals are truly inverses, then wouldn't an integral just be an antiderivative? What do I mean by antiderivative? Well, undo a derivative, right? So today, the bulk of your homework is going to be practicing undoing derivatives. So I have an example up here. The derivative of a constant is 0. Right? So what's the integral of 0? Some constant, because I undo the derivative. So it's crazy that somehow integrals and antiderivatives are related. So we're taking a step back from area for today. Tomorrow we'll revisit how you could actually use this to find area. We're just mental noting that, hey, if they're inverses, then an antiderivative should be helpful. If the derivative of x is 1, then the antiderivative of 1 would be x plus a constant. Why plus a constant? What would happen if I took the derivative of that right hand x plus c? The c would go away. So would you agree that with any integral, I'm going to get a constant? Possibly. That's going to be your u primes of the next gateway exam, or your plus c's. To always remember to put those plus c's. But it's because anytime you take a derivative, all the constants fall out. So when you go backwards, you always have to take into account that there could have been a constant there. Maybe there was, maybe there wasn't, but there could have been. What do you think the next one is? Okay, x squared. What do you think the antiderivative of x squared would be? One-third x cubed. Why? Is he right? Do the derivative of it. Write it down. Write down 1/3 x cubed. What's the derivative of 1/3 x cubed? Now, what was your thought process, Hunter? Okay, I gotta get 1 as a coefficient, so you want the power and the constant to cancel. And then you're going to reduce the constant, or the power by 1, so you... Right? So this is the power rule. You just took this on your gateway exam last Friday, right? The power rule for derivatives is that you bring the power down, reduce the power by 1, right? In integration, you raise the power by 1, and you divide by that new power. So if we have x squared, we're going to make it x cubed, and then we're going to divide by 3, or do 1/3 x cubed. Raise the power to 1 more, and then divide by the new power. So u to the n plus 1 divided by n plus 1, or multiplied by 1 over n plus 1, either way. Plus c. Don't forget plus c. Why plus c? Right, I've got to take into account that there could have been a constant there. If I am saying whose derivative is x squared, well, it could be 1/3 x cubed. It could be 1/3 x cubed plus 5, 1/3 x cubed plus 10. I don't know. I lost a constant in differentiation, so that's where I'll have to take that into account. If the derivative of e to the u is e to the u, then the integral of e to the u is e to the u. Right? You notice we are ignoring the chain rule at this point. We will discuss that later. A later discussion on how to deal with things other than just a u or other than just an x. And what you will notice is on those right-hand equations that use u, they have the variable as u, kind of like dx. So that's why they don't have anything taken into account with the u. Maybe u primes or anything. If the derivative of natural log of the absolute value is u prime over u, or if you take that to a more simplistic approach, if it were just x, it would be 1 over u, then the antiderivative of 1 over u is natural log of the absolute value of u. The reason you have to have an absolute value in there is because a logarithm can't be negative. Now, you haven't thought about the absolute value up until this point because it started as a logarithm, so it wouldn't have a problem. But since it's not starting as a logarithm, we have to be careful and not put negatives in logarithms. So that's where the absolute value comes into play. We'll talk about that more later. Is everyone to e to the u? The derivative of sine of u is cosine of u, then the antiderivative of cosine of u is sine of u. Right? What am I asking myself when I answer the question on the right? When I do the integral of cosine of u, or the antiderivative of cosine of u, what's my brain going to ask? What function has a derivative that is cosine? Sine. So that's what the question you're asking on that right-hand piece is. What function has a derivative that's this answer? What function has a derivative that equals sine? Well, negative cosine. So you'll notice the negatives are a little bit backwards on these, which they should be, because derivatives. Now you could do the antiderivative of negative sine, which would be cosine. But if I just ask you what's the antiderivative of sine, you would have to ask yourself what function gives you sine as its derivative. Does that make sense? Secant u, tangent u, secant u. Then there's a complicated one, tan inverse. And they even made it more complicated. If they'd left the a as a 1, it'd be more straightforward. Look at your calculus helper for the rest of the rules. Have you noticed that other part of your calculus helper? The bottom? Where the derivative rules are, there's a whole set of integral rules as well. The one problem with integration that you need to know is that there are basically an infinite number of integration rules. Remember me telling you there's no product rule and no quotient rule for integration? Those didn't work yesterday. We didn't have a rule for that. That's going to cause us problems. And we'll continue to talk about that as we learn how to do anti-differentiation. But that's going to cause us problems. How big of problems? Now this is in no way, shape, or form something you need to have memorized. What do you need to have memorized eventually? What's on your calculus helper, right? This is the back of a college calculus textbook. And it is titled A Brief Table of Integrals. And I find that quite hilarious. This is page 1. This is page 2. This is page 3. Page 4. Brief table. Well, what I'm telling you is there are essentially infinitely many rules for integration because we don't have a product or quotient rule. So for every individual function, it could have its very own antiderivative. Now we will learn some tricks of the trade to get here. And again, by no way, shape, or form are you expected to know any of these. What you are expected to know are essentially the ones you already know backwards. So, anyway, fun times. Okay, so how is that going to help me? This is what your homework will look like. I want to find the antiderivative of x to the fifth minus 3x plus 4. We may need to use some of our rules from yesterday to make it easier. But we may not. So this is what your homework looks like. So don't stress about our brief table of integrals. Your textbook doesn't have one of those in it. I don't believe. Okay. So this looks a little intimidating because it has three pieces. From yesterday with pluses and minuses in between, what can I do? I can split them up. You don't have to. In fact, this is probably the last time you would ever split a polynomial up, but you can. I can do the antiderivative of x to the fifth, the antiderivative of 3x, and the antiderivative of 4. So, how would I do x to the fifth? Good. Where in the world did you get 16x to the sixth? Good. I raise the power 1, divide by the new power.
Okay, so that's why when I was talking about the 1/3 x cubed with the x squared. That's
okay.
why
So I want to know what has a derivative that's x to the fifth. So if I took the derivative of something, what would give me x to the fifth?
the one that gives you x.
Doesn't it? Take the derivative.
Yeah.
Okay. Now, are you going to want to rack your brain that hard every time? Probably not. And that's why we learned the rule. And the rule is, if we have the integral of u to the n, that is 1 over n plus 1, u to the n plus 1. Right? That's what the rule said. So I'm going to add 1 to the power and divide by the new power. You see how that rule works? Negative 3x. You could leave it and consider it a power rule. You could use it as a constant times x rule. It doesn't matter. What's the power on the x? 1. So I could rewrite this, and again, you will probably never do this again because you'll get fast at this. Right, the negative 3 is just a constant, so I'm just going to kind of leave it hanging out there. Minus 3. What do I get if I add 1 to the power of 1? So I get x squared, and I'm going to divide by 2. So I have 3 halves x squared. Does that make sense? So I'm just following those rules. The constant just stays there, just like with derivatives. So this was power 1. 1 plus 1 is 2. You see that?
So like
1 plus 1 is 2, and then I divide by the 2.
okay, because it's like it's the inverse again, so instead of like multiplying, you divide.
Yep, and check it. Can you ever get these wrong without knowing you're wrong? Look, do the derivative. What's the derivative of that piece?
3.
Oh, I did a good job. If that's not the case, you messed up. Does that make sense? What about 4? What's the antiderivative of 4? 4x. Why? Because the derivative of 4x is 4. It's weird. We're thinking backwards, but you'll get the hang of it. And then I'm always going to put a plus c. Yes, absolutely. Like I said, it's even hard for me to write that down. My brain does not want to write that, but it's new, so the simplified form of 5 sine of x is just, hey, move the constant out. Again, eventually you won't do that. Your brain will just take care of the constant like it does with differentiation. But for now, we'll move it. What function's derivative is sine of x? Negative cosine. Why negative cosine? Because the derivative of cosine is negative sine, so negative negative will give you that positive. Strange, but sure enough. And you'll notice that's what the rule said. You don't have to come up with these rules. It'll hurt your brain today. You'll get better tomorrow. Okay, I'm going to rewrite this one. This is probably the most commonly messed up integral because everyone wants to make it a power rule. But if I rewrite it, 4 times the integral of 1 over x. What is the very special rule for 1 over x? What is 1 over x the derivative of?
Like, I was going to say
natural log. That's right. So natural log. Now the new thing is you do have to put an absolute value in that x because I don't know if x was positive or negative. I cannot have a negative in a logarithm, so I've got to take care of that piece. Oh yes, thank you very much. 4 times natural log of x. I want to show you something really quick. Because we're about to do some problems where we deal with negative exponents and whatnot. If you wrote this with a negative exponent, it would be 4x to the negative 1. What would you get if you tried to do a power rule? What's negative 1 plus 1? 0. What's anything to the 0 power? 1. And then you'd divide by 0, wouldn't you? There's all kinds of doesn't make sense. But it's the derivative of that is sure not 4 over x, right? So a power rule, there's only one case where it doesn't work, and that's to the negative first power. And that's because the antiderivative of a negative first power is a logarithm. So you might want to star that one in your notes. It's one that people like to mess up. Okay, 1/4 cosecant squared x. What is the antiderivative of cosecant squared? What has a derivative that is cosecant squared? Cotangent. But isn't the derivative of cotangent negative cosecant squared? So what do?
Negative.
Go to negative. Check it. What's the derivative of negative 1/4 cotangent of x? Works, right? When you're working your homework tonight, no, forever that won't be the case, but when you're working your homework tonight, check them all. Every single one, do the derivative really quick. Your homework tonight's pretty short, so won't kill you to check it. Okay, this one I really need a simplified form, because do I have a quotient rule for integrals? No. So if I can't simplify this with algebra, I'm in big trouble. Can I simplify it with algebra? How does it simplify? 5x minus 2 plus 5 over x. You can write it as 5x to the negative 1, although I do like the decision not to. Why do I like the decision not to? Since it's x to the negative 1, it would be a natural log, so it's up to you. But if you see x to the negative 1, remember that that's a natural log, antiderivative. What's the antiderivative of 5x? And notice I haven't broken it down quite as much, but you're getting better. So 5x. What is the antiderivative? 5 over 2x squared. How in the world did she get that? Good. Add 1 to the power. Divide by the new power. And the 5's just hanging out. What about the minus 2? Minus 2x. What about the 5 over x? Plus 5 natural log of the absolute value of x. Plus c. Don't forget your plus c. Okay, the next one's tough because I have to use some nasty algebra. Again, I do not have a quotient rule. If I can't simplify this with algebra, for today I would be stuck. Can I simplify x squared divided by the square root of x? Okay, this is x to the 1/2 power. Would you agree? Can I subtract exponents and get a single x? So x squared divided by x to the 1/2. 2 minus 1/2 is 1.5 or 3 halves.
So you did x squared divided by x to the negative 1/2? Is that what you did?
No, divided by x to the 1/2. And when you have, you know your properties of exponents note card from Miss Lowe's class or my class, one of the two? When you have two things with the same base, on top and bottom, you subtract exponents. So that's what we do. Cosine of x, I didn't mean to put a dot there. Sorry about that. What's the, hold on, you're right. Let me leave it for a second. This is just simplified. I haven't done any antiderivatives yet. Okay. It's a fraction, but is it a power? Can I use power rule? The only time I can't use power rule is if it's -1 exponent, then it's a logarithm. Every other exponent, I just use power rule. Can I add 1 to 3 halves? And what do I get if I add 1 to 3 halves? 5 halves. What do I divide by? I divide by 5 halves. What's the same as dividing by 5 halves? Multiplying by 2/5. Would that make sense? Would the 5 halves and the 2/5 cancel when I did the derivative? Would I get x to the 3 halves when I subtracted 1? See how I'm checking by doing a derivative in my head, especially while I'm new at this? And what is the antiderivative of cosine? Sine of x's derivative. Would it? Take the derivative. What's the derivative of sine? It's weird because it's backwards. Everything, it's like topsy-turvy land today. This last one's really weird because can I simplify it? Can I simplify the last one? No. So there better be a rule for that, or I'm in big trouble. So look close. Is there anything that is the derivative of? Tan inverse, isn't it? It is just a rule in its very own self. It's a weird rule, but it's just a rule. And it is tan inverse, right? Look at derivative rules. So it's a weird rule. It's one we're not as familiar with. It doesn't come up as often. But there is no simplification needed at all. It is just tan inverse of x plus c. I have this down here to talk about, but haven't we been doing this the whole time? Checking them? How do you check them? Take the derivative. Right? If it works out, you did a good job. If it doesn't, try again. Okay, your homework for tonight is page 1 of this worksheet. Not even the back, like just the front page of this worksheet. Right here. And 1 through 11 odd on page 342. What do you know about odds in your textbook? 1 through 11 odd, and this front page here.